Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book Retrolinear. The subject of this lecture is sets of functions as vector spaces. If you have two sets x and y, then we use this notation f colon x arrow y to mean that we have a function from x to y. X is the domain of the function. Those are the things that you have to be able to plug into the function. Everything in x needs to be able to be plugged into the function f. Y is the codomain, or the target set is the canvas on which you throw elements of x. You don't need to be sending something to every element of y, but y is the place where the elements of x end up. The function from x to y is the rule that assigns to each element of x one element of y. Another name for a function is a map, and the way we like to think about it is that x is on this side, y is on that side, and f is sending elements from x to y. And for example, alpha is mapped to f of alpha, beta is mapped to f of beta. What's not allowed is that one element of x goes to two elements. That's a no. If you have that, you do not have a function. On the other hand, it's quite fine to have two elements go to the same element. I have a whole set of videos on functions. For more detail, watch them. I want to talk about sets of functions. R is going to be the set of real numbers, and FRR, or maybe a better notation, R raised to the power R, is going to denote the set of all functions from R to R. Not just one of them, but all real valued functions on R. Functions on R means that the domain is R. Real valued means the values you're getting out are real. For example, sine of x is a function from the reals to reals. You plug in any real number you like, and you'll get back a real number. You don't get back all real numbers. You only get back numbers between -1 and 1, but that's okay. 3x squared plus 5 is also a function from R to R. 1 over x minus 1 is not, because you can't plug in 1. 1 over x minus 1 is an element of a different function space if you take the domain to be all real numbers except for 1, and the codomain can be R, and 1 over x minus 1 is an element of that. Each function is one element of FRR. This FRR is a set of functions, and each function is just one element. That whole thing, sine of x, is just one element of this function space. More generally, f of xy is going to be all functions from x to y. X is the domain and y is the codomain. What games can we play in this FRR? If we walk into the set of all functions, what can we do with them? There's lots of things we can do with them, but we are going to focus on the two things that a vector space needs, and that's addition and scalar multiplication. So if you want to be in a vector space, you need addition and scalar multiplication. We can add functions. For example, y equals sine of x, that's this function, and y equals x is that other function, and we can add them, and you can get the function x plus sine of x. And you can do that with any two functions. If you have a function in FRR and another function in FRR and you add them, you get yet a third function in FRR. You can also multiply functions with scalars. For example, y equals sine of x and y equals 3 times sine of x. That's another function from R to R. By multiplying a function by a scalar, by a number, you can get another function in FRR. There's other things you can do with functions as well. For example, you can multiply them. You can divide them, but if the function you divide by has a 0, you might not quite stay in the same function space. But we're not interested in those. We're only interested in addition and scalar multiplication. And if we think of it that way, then we have a vector space over R. Over R means that the scalars are real numbers. Could the scalars be something else? Yes, they could be. And that's a subject of other videos. What does it mean to be a vector space? It means that you have addition and scalar multiplication, and they follow the rules of a vector space. And what are those rules? If you have two functions f and g, it doesn't matter which way you add them. It's commutative. It's also associative. F of x plus g of x, if you add those, and then add h of x, that's the same as if you take f of x and add it to g of x plus h of x. It doesn't matter which way you put those parentheses. You have the zero function, the x-axis, y equals 0. And what's special about that? It has the property that when you add it to other functions, nothing happens. That's called the zero of this vector space. And every function has an additive inverse. If there's some other function that if you add it to it, you get that 0. So sine of x and minus sine of x, if you add them, you get the 0 function. Scalar multiplication also has these semi-obvious properties. For example, if you take a scalar, real number alpha, and multiply it by f of x plus g of x, you can distribute that in, and you can have alpha f of x plus alpha g of x. Also, alpha plus beta, two scalars. Alpha plus beta times f of x is the same as alpha f of x plus beta f of x. You can also distribute the scalars in that way. And alpha beta times f of x is the same as alpha times beta f of x. And finally, the most silly of all, if you take the number 1 and multiply it by function, you get your function function back. Now, why am I focusing on these? These are the properties of a vector space, and these are the properties that function spaces have in common with things like Rn, with matrices, with polynomials, and so forth. And the purpose of linear algebra is to abstract out these common properties and say that we have a situation where we have a non-empty set and we have addition and scalar multiplication. Those are the games we can play, and those games have certain rules, and these are the rules that we want to focus on. I don't have to have functions whose domain is R. I can have x be any set, and I can have all the functions from x to r. For example, if you take x to be r2, a function from r2 to r might be the function that takes the point ab and sends it to a squared plus 47b. fxr is also a vector space over r because you can add two functions whose domain is x and gives you values in r, and the same thing with scalar multiplication. And the same rules still apply. In fact, more generally, and in a first encounter with the linear algebra, you can ignore this. If X is any set, F is any field, the field is a place where you can add, you can subtract, you can multiply, and you can divide by non-zero elements. And fields are things that can be scalars. In the first reading of linear algebra, scalars are real numbers, but in a second reading, they can be elements of any field. We have videos about fields later in this series. If V is any vector space over F, so V is any kind of a vector space whose scalars are F, then if you look at the functions from X to V, then that's also a vector space. So you start with a vector space, and you start with any set and find functions from that set to your vector space, and you get a new vector space. I also want to say that this fxr, this vector space of functions from X to R, actually generalizes our prototypical example of a vector space, Rn. Rn is the vector space of n tuples. You can add n tuples, you can multiply by scalars. I have a whole video on Rn as an example of a vector space, and you should watch that. But I want to say that fxr actually directly generalizes that. For example, elements of R4 are just 4 tuples. Lists of 4 ordered numbers. You can write them as column vectors with 4 numbers in them. One particular element of R4, for example, is the one that has 1/4 pi minus 5 and 47 as its entries. This is one element, not 4 elements of R4. And you can think of this one element as a function. And how can you do that? You can think of it as a function that goes from the set 1, 2, 3, 4 to R. This function is defined by f of 1 goes to 1/4. F of 2 is pi. The way I think about that is that in the first position, I have 1/4. In the second position, I have pi. In the third position, I have minus 5. And in the fourth position, I have 47. So this function is actually telling me exactly the same information as that one element of R4. So if I let bracket 4 to be 1, 2, 3, 4, then R4 really is the same as all the functions from 1, 2, 3, 4 to R. Any function from 1, 2, 3, 4 to R gives you an element of R4, and any element of R4 gives you a function from 1, 2, 3, 4 to R. So these two things are the same. By analogy, instead of FRR, I can write R to R. The functions from a set with 4 elements to R was R4, and now the set of functions from all real numbers to real numbers is R to R. And more generally, the set of functions from a set X to a vector space V, one can write as V to the X. This is the end of this lecture. Watch my other videos on examples of vector spaces and then the theory of vector spaces. Keep hydrated at all times. Like my videos if you like them. And if you like to be subjected to more math videos, then please subscribe to my channel. See you in the next lecture.